seawater or salt water is water from a sea or ocean. On average, seawater in the world's oceans has a salinity of about 3.5%. This means that every kilogram of seawater has approximately 35 grams of dissolved salt and chloride ions. Average density at the surface is 1.025 gram per milliliter. Seawater is denser than both fresh water and pure water, because the dissolved salts add mass without contributing significantly to the volume. The freezing point of seawater decreases as salt concentration increases. At typical salinity it freezes at about a 2 degrees Celsius. The coldest seawater ever recorded was in 2010, in a stream under an Antarctic glacier, and measured a 2.6 degrees Celsius. Seawater pH is typically limited to a range between 7.5 and 8.4, and the speed of sound in seawater is, on average, roughly 1,500 ams. Geochemistry: the thermal conductivity of seawater is 0.6 with Mk at 25 degrees Celsius and a salinity of 35 gram per kilogram. The thermal conductivity decreases with increasing salinity and increases with increasing temperature. Salinity: although the vast majority of seawater has a salinity of between 3.1% and 3.8%, seawater is not uniformly saline throughout the world. Where mixing occurs with freshwater runoff from river mouths or near melting glaciers, seawater can be substantially less saline. The most saline open sea is the Red Sea, where high rates of evaporation, low precipitation and river inflow, and confined circulation result in unusually salty water. The salinity in isolated bodies of water can be considerably greater still. The density of surface seawater ranges from about 1020 to 1029 a kilogram per meter 3, depending on the temperature and salinity. Deep in the ocean, under high pressure, seawater can reach a density of 1050 a kilogram per meter 3 or higher. Seawater pH is limited to the range 7.5 and 8.4. The speed of sound in seawater is about 1,500 ams, and varies with water temperature, salinity, and pressure. Human impacts: climate change, rising atmospheric carbon dioxide, excess nutrients, and pollution in many forms are altering global oceanic geochemistry. Rates of change for some aspects greatly exceed those in the historical and recent geological record. Major trends include an increasing acidity, reduced subsurface oxygen in both near-shore and pelagic waters, rising coastal nitrogen levels, and widespread increases in mercury and persistent organic pollutants. Most of these perturbations are tied either directly or indirectly to human fossil fuel combustion, fertilizer, and industrial activity. Concentrations are projected to grow in coming decades, with negative impacts on ocean biota and other marine resources. Compositional differences from freshwater: seawater contains more dissolved ions than all types of freshwater. However, the ratios of solutes differ dramatically. For instance, although seawater contains about 2.8 times more bicarbonate than river water based on molarity, the percentage of bicarbonate in seawater as a ratio of all dissolved ions is far lower than in river water. Bicarbonate ions also constitute 48% of river water solutes but only 0.14% of all seawater ions. Differences like these are due to the varying residence times of seawater solutes. Sodium and chlorine have very long residence times, while calcium tends to precipitate much more quickly. The most abundant dissolved ions in seawater are sodium, chloride, magnesium, sulfate and calcium. Microbial components: research in 1957 by the Scripps Institution of Oceanography sampled water in both pelagic and neritic locations in the Pacific Ocean. Direct microscopic counts and cultures were used, the direct counts in some cases showing up to 10,000 times that obtained from cultures. These differences were attributed to the occurrence of bacteria in aggregates, selective effects of the culture media, and the presence of inactive cells. A marked reduction in bacterial culture numbers was noted below the thermocline, but not by direct microscopic observation. Large numbers of spirelli-like forms were seen by microscope but not under cultivation. The disparity in numbers obtained by the two methods is well known in this and other fields. In the 1990s, improved techniques of detection and identification of microbes by probing just small snippets of DNA, enabled researchers taking part in the census of marine life to identify thousands of previously unknown microbes usually present only in small numbers. This revealed a far greater diversity than previously suspected, so that a litre of seawater may hold more than 20,000 species. Dr. Mitchell Sojin from the Marine Biological Laboratory feels that the number of different kinds of bacteria in the oceans could eclipse 5 to 10 million. Bacteria are found at all depths in the water column, as well as in the sediments, some being aerobic, others anaerobic. Most are free-swimming, but some exist as symbionts within other organisms, examples of these being bioluminescent bacteria. Cyanobacteria played an important role in the evolution of ocean processes, enabling the development of stromatolites and oxygen in the atmosphere. Some bacteria interact with diatoms, and form a critical link in the cycling of silicon in the ocean. One anaerobic species, the Margarita nambensis, plays an important part in the breakdown of hydrogen sulfide eruptions from diatomaceous sediments off the Namibian coast, and generated by high rates of phytoplankton growth in the Benguela Current upwelling zone, eventually falling to the sea floor. Bacteria like Archaea surprise marine microbiologists by their survival and thriving in extreme environments, such as the hydrothermal vents on the ocean floor. Alcohol-tolerant marine bacteria such as Pseudomonas and Vibrio spp survive in a pH range of 7.3 to 10.6, while some species will grow only at penthouse 10 to 10.6. Archaea also exist in pelagic waters and may constitute as much as half the ocean's biomass, clearly playing an important part in oceanic processes. In 2000, sediments from the ocean floor revealed a species of Archaea that breaks down methane, an important greenhouse gas and a major contributor to atmospheric warming. Some bacteria break down the rocks of the sea floor, influencing seawater chemistry. Oil spills, and runoff containing human sewage and chemical pollutants have a marked effect on microbial life in the vicinity, as well as harboring pathogens and toxins affecting all forms of marine life. The protist dinoflagellates may at certain times undergo population explosions called blooms or red tides, often after human-caused pollution. The process may produce metabolites known as biotoxins, which move along the ocean food chain, tainting higher-order animal consumers. Pandora virus salinus, a species of very large virus, with a genome much larger than that of any other virus species, was discovered in 2013. Like the other very large viruses Mimivirus and Megavirus, Pandora virus infects amoebas, but its genome, containing 1.9 to 2.5 megabases of DNA, is twice as large as that of Megavirus, and it differs greatly from the other large viruses in appearance and in genome structure. In 2013, researchers from Aberdeen University announced that they were starting a hunt for undiscovered chemicals in organisms that has evolved in deep-sea trenches, hoping to find the next generation of antibiotics, anticipating an antibiotic apocalypse with a dearth of new infection-fighting drugs. The EU-funded research will start in the Atacama Trench and then move on to search trenches off New Zealand and Antarctica. The ocean has a long history of human waste disposal on the assumption that its vast size makes it capable of absorbing and diluting all noxious material. While this may be true on a small scale, the large amounts of sewage routinely dumped had damaged many coastal ecosystems, and rendered them life-threatening. Pathogenic viruses and bacteria occur in such waters, such as Escherichia coli, Vibrio cholerae, the cause of cholera, hepatitis A, hepatitis E and polio, along with protozoans causing giardiasis and cryptosporidiosis. These pathogens are routinely present in the ballast water of large vessels, and are widely spread when the ballast is discharged. Origin. Scientific theories behind the origins of sea salt started with Sir Edmund Halley in 1715, who proposed that salt and other minerals were carried into the sea by rivers after rainfall washed it out of the ground. Upon reaching the ocean, these salts concentrated as more salt arrived over time. Halley noted that most lakes that don't Euro unregistered trademark T have ocean outlets, have high salt content. Halley termed this process continental weathering. Halley's theory was partly correct. In addition, sodium leached out of the ocean floor when the ocean formed. The presence of salty unregistered trademark S other dominant ion, chloride, results from outgassing of chloride with other gases from Earth's interior via volcanoes and hydrothermal vents. The sodium and chloride ions subsequently became the most abundant constituents of sea salt. Ocean salinity has been stable for billions of years, most likely as a consequence of a chemical tectonic system which removes as much salt as is deposited. For instance, sodium and chloride sinks include evaporite deposits, poor water burial, and reactions with seafloor basalts. Human consumption. Accidentally consuming small quantities of clean seawater is not harmful, especially if the seawater is taken along with a larger quantity of fresh water. However, drinking seawater to maintain hydration is counterproductive. More water must be excreted to eliminate the salt than the amount of water from the seawater itself. The renal system actively regulates sodium chloride in the blood within a very narrow range around 9 grams per litre. In most open waters concentrations vary somewhat around typical values of about 3.5%, far higher than the body can tolerate and most beyond what the kidney can process. A point frequently overlooked, in claims that the kidney can excrete NaCl in Baltic concentrations, is that the gut cannot absorb water at such concentrations, so that there is no benefit in drinking such water. Drinking seawater temporarily increases blood unregistered trademark NaCl concentration. This signals the kidney to excrete sodium, but seawater unregistered trademark S sodium concentration is above the kidney unregistered trademark S maximum concentrating ability. Eventually the blood unregistered trademark S sodium concentration rises to toxic levels, removing water from cells and interfering with nerve conduction, ultimately producing fatal seizure and heart arrhythmia. Survival manuals consistently advise against drinking seawater. A summary of 163 life raft voyages estimated the risk of death at 39% for those who drank seawater, compared to 3% for those who did not. The effect of seawater intake on rats confirmed the negative effects of drinking seawater when dehydrated. However, the regulation of the uptake of seawater salts may be possible through the colon. The mother of the Robertson family who were cast away for 38 days in 1972, proposed the feasibility of hydration through unpotable water enemas. The temptation to drink seawater was greatest for sailors who had expended their supply of fresh water, and were unable to capture enough rainwater for drinking. This frustration was described famously by a line from Samuel Taylor Coleridge's The Rime of the Ancient Mariner. Water, water, everywhere, and all the boards did shrink. Water, water, everywhere, nor any drop to drink. Although humans cannot survive on seawater, some people claim that up to 2 cups a day, mixed with fresh water in a 2-to-3 ratio, produces no ill effect. The French physician Alain Bombard survived an ocean crossing in a small Zodiac rubber boat using mainly raw fish meat, which contains about 40% water, as well as small amounts of seawater and other provisions harvested from the ocean. His findings were challenged, but an alternative explanation was not given. In Kentucky, Thor Heyerdahl reported drinking seawater mixed with fresh in a 40/60% ratio. A few years later another adventurer named William Willis claimed to have drunk 2 cups of seawater and 1 cup of fresh per day for 70 days without ill effect when he lost part of his water supply. During the 18th century, Richard Russell advocated the practice's medical use in the UK, and Rena copyright Quinton expanded the advocation of the practice other countries, notably France, in the 20th century. Currently, the practice is widely used in Nicaragua and other countries, supposedly taking advantage of the latest medical discoveries. Most ocean-going vessels desalinate potable water from seawater using processes such as vacuum distillation or multi-stage flash distillation in an evaporator, or more recently by reverse osmosis. These energy-intensive processes were not usually available during the Age of Sail. Larger sailing warships with large crews, such as Nelson's HMSA Victory, were fitted with distilling apparati in their galleys. Other land and marine animals such as fish, whales, sea turtles, penguins and others can adapt to a high saline habitat. For example, the kidney of the desert rat can concentrate sodium far more efficiently than the human kidney. Basic ASTM International had defined an international standard for making artificial seawater, ASTM D1141-98. It is used in many research testing labs as a reproducible solution for seawater, such as tests on corrosion, oil contamination, and detergency evaluation. See also, artificial seawater, brine, freshwater, saline water, salinity, sea ice, sea salt, seawater gel, seawater pH, Merlin circulation, CORA dataset global ocean salinity, external links, tables and software for thermophysical properties of seawater, MIT, physical properties of seawater, notes.